Well, good evening, everyone, and welcome to this presentation of the what will normally be the GOTAM meeting. Let me see what we've got. So I hope everybody enjoyed the spectacular bank holiday weather, which was most unusual for a bank holiday, I have to say. Got a few things coming up. There's a partial eclipse of the sun next week, but only a small one, so we'll only see a little bit of it. I think this next week on Thursday, 2 weeks on Thursday, we have the more informal meeting, and this time it's probably going to be on the Milky Way, I think, if we get everything together. The following meeting in July will be Chris Arity talking about, it's just gone straight out of my bed. Oh, the JUICE mission to Jupiter. So that would be really interesting. And in August, we are still hoping to go ahead, and it looks quite likely now with the barbecue in, that's the 7th of August, I think, the second Sunday of August. And hopefully that will be at the observatory site, which will be open and ready for visitors. So that's mostly what we've got for tonight in news, but otherwise the main event, Professor Ian Morison, who's come back again to talk to us, which we're very grateful for. It was almost a year ago that he last visited us to give a remote talk. Unfortunately, it's still remote this time, but we can cross our fingers. Maybe he'll come back again next year in the flesh. Who knows? Anyway, tonight, very big welcome to Ian and his talk on the Harbingers of Doom. Over to you, Ian. You'll need to switch.
Good evening, everybody. Let me share my screen. And I want to have this one, and I want to go from the beginning. I hope that's visible. Thumbs up, Julian. Thank you. Well, good evening. Yeah, I'm sorry I'm not with you. I've always enjoyed my trips across to you at Nottingham. It's been a nice evening out. So maybe, as you said, sometime next year. You never know. Anyway, what's this all about? Well, in the past, people got quite worried that our Earth perhaps would be rent asunder by the impact. I think in this case it looks like a comet, but they're not the only things. Asteroids, things we call near-Earth objects, could be equally bad for us. So I'd like to talk about that this evening. Well, here we go. Should we be afraid? Well, I hope not, but you never know. Anyway, let's see how we get on. These are two pictures I took of the moon a little while ago now, but that's ample evidence of impact, some of them very large, forming these wonderful basins here like Mare Serenitatis and Mare Tranquillitatis. I hope you can see Apollo 11, it's about there, and Oceanus Propylarum all over here. Well, there was a lot of controversy, I like controversy, about how these impact craters were formed. Patrick Moore was quite convinced they were formed by eruptions, and that's because they're all basically round. And he said because impacting objects would come in from all sorts of angles, you should have elliptical shaped craters rather than round ones. Well, we now know that the impacts you get are called hypervelocity. Here are a couple of nice pictures of close up. And notice here, you see some of the mountains in the heart of this crater and the terrace walls. They're quite common. So why is this? Well, they've done experiments, firing balls into surfaces like this to see what happens. And it doesn't really matter too much what the angle is, you still get a circular depression. And this is why. Because it's what's called a hypervelocity impact. Whatever the object is, burrows down through the surface to quite some depth and then explodes. So it doesn't really matter too much which angle the bolide, whatever it is, has come in from. And that's giving you an idea of what happens. And you get various sort of shocks and upwelling, and you do finally finish up with a little bit of a mountain chain right in the center of one of these impacts, if it's large enough. If it's a small impact, then they're beautifully round and smooth. So you see what's happening there. Well, we have lots of craters on Earth. And one of the largest one I'm sure you know is the Barringer crater, otherwise known the Meteor crater in America. One of the largest. I'd love to go and see that, but I haven't actually done that. But there are some remnants of it down under here. That's quite a big one. Nice view of it there. However, we do have craters in Europe, and perhaps they're not so well known to people. There's a couple of pictures there, a very small one there in Poland, but a rather larger one there in Finland. And there are, in fact, two quite large craters in Germany, which I was able to visit some years ago. First of all, the Rice crater, and then there's a second one we'll come to. It was a lovely clear day when I was here, so using a telephoto lens, I was actually able to photograph the far rim. It's actually pretty big, as we shall see. There is a nice little town called Nordlingen there, and the stone is interesting because it contains millions of tiny diamonds, each about 0.2 millimeters in diameter. And essentially, it's thought the impact produced around 72,000 tons of diamonds when it impacted a local graphite deposit. Because one way of making diamonds now, of course, is to compress carbon very, very much. Then the Steinheim crater is a small one. They're quite close, and it's thought that they were actually result of a pair of co-rotating objects. This is much smaller. That's a sort of a view of it there. Nice little town here, and here is the upswelling. And that's a photograph I took when I was there. And the material is incredibly chaotic. It's being crushed and torn asunder by the impact of the object that caused the crater. The Rice crater is about 1.5 kilometers, the size of the impactor. The Steinheim one, much smaller, 150 meters, coming in at an impact velocity of about 20 kilometers per second. And I'll talk about impact velocities a bit later on. And they believe the energy which formed the Rice crater was 1.8 million Hiroshima bombs. And they both date from about 14.7 million years ago. And it's thought they're the source of the rather lovely moldavite tektites that are found in Bohemia. And there's a little picture of one there on the right, greenish object. Now, of course, one of the major events was the Chicxulub event. It was caused by an impacting object about 11 kilometers in diameter, some 66 million years ago. It caused what's called a mass extinction. And in this one, about 75% of plants and animals became extinct. That's not the worst. One of them much earlier, I think they said about 90% became extinct. And this is said to have released 2 million times more energy than the most powerful H-bomb ever detonated. And that is quite a lot. Well, it is at the top end of the Yucatan Peninsula. I've actually sailed across it. So actually, we're going to a port here to go and have a look at some of the wonderful cities here that exist in the jungle. It's 92 kilometers in diameter, 12 kilometers in depth. I'm sure many of you know these things. It was discovered when they were prospecting for oil, and they discovered these circular objects, and there's a sort of a scan on the right-hand side showing you some idea of what's under the water largely. What is interesting is that they've discovered an iridium layer that dates from about the same time. Now, iridium is not very common on the Earth, but in this layer, the concentration is very high. It's thought that there was a lot of iridium in the impactor. It's not totally known whether it was an asteroid or a comet. And that produced a lot of dust that fell on the ground and formed, after compression, this layer. So that's rather nice proof that there was, in fact, an impact from outside our solar, well, outside certainly the sun and the Earth system. We think it was equivalent to a magnitude 12 earthquake, and that itself triggered magnitude 9 earthquakes. Now, it's a logarithmic scale, so when you talk about a magnitude 7 earthquake, 12 is an awful lot more than that. It's also thought it may have triggered the lava flows of the Deccan Flats in India, and they're down there. There's a plateau. It's thought when they actually were formed, a lot of CO2 was released, and although initially after the impact, all the dust in the atmosphere would have cooled the Earth, once that died away, the extra CO2 would have made the Earth fairly warm for a while. And that wasn't caused by us, of course. It could well be that that impact was at least a major cause of the demise of the dinosaurs. Obviously, a lot of the vegetation that they would eat, certainly some of them would eat, had gone. It may be also the CO2 meant that the atmosphere was less good for them than one would like, and they may have suffered a bit from lack of oxygen. Anyway, that was a very good thing, because of course, with their demise, it allowed little mammals to gradually evolve into us. So otherwise, we'd perhaps not be here, and I wouldn't be talking to you. These global extinctions are very good because they actually stimulate evolution. And it's fine if you have them, say, every 100 million years. It wouldn't be good if we had them every 10 million years. If that were the case, we wouldn't be here. And so luckily, it's obvious that these major impact events don't happen very often on Earth, for which we should be very grateful. Well, the largest, not quite an impact, but the largest event in recorded history is that of Tunguska in 1908. And it actually happened in Siberia, and that's where you see it. Happily, not many people lived there. I think only about 3 people died. But notice that it's actually on the same latitude, pretty much, as St. Petersburg. Had it, I think, happened 2 hours later when the Earth would have rotated round, St. Petersburg and all the people there would have been destroyed. There's the explosion epicenter. And again, there's not a lot around some of the named places there. And there's actually a railway that is not too far away, which is the Trans-Siberian Railway. Very cold up there, and that meant that things basically stayed pretty much as they were. And it was a very long time before people went to the explosion epicenter to see what was there. This is the idea of what happened. If I just click through this, it was an airburst. Because a thing coming in very fast actually finds the atmosphere is pretty dense. And that airburst, the shock wave traveling south from it or below from it down here, basically flattened all of the trees. I think around 88 million trees were flattened. And there you can actually, if you cut across one of the trees that is still there, it was a fairly normal tree until about 1908, and can you see it's obviously fallen on its side, and the growth has been quite asymmetrical since that time. So it's believed to be the result of an airburst of a stony meteorite about 100 meters across. And it's the largest impact, as I said, recorded in history, and a couple of hours later, as the Earth had rotated, it could have destroyed St. Petersburg. The actual shape of the fan, really, of the trees formed a butterfly shape. And that let people work out quite a bit about its actual trajectory into the Earth's atmosphere. And there's just a couple of artists' impressions of how it might have looked. Apparently only 3 people died, which is a good thing, really. Now, I mentioned that I'd said something about impact speed. And I found this quite interesting. It was a long time before I understood this, seriously. And I can't spell speed, so we'll move on very quickly. Now, supposing the Earth was stationary, if any object comes in from a far distance, say infinity, it would actually hit the Earth with a velocity of 11 kilometers per second, which is the Earth's escape velocity. So just in the same way, you need to have a velocity of 11 kilometers per second to get away from the Earth, to escape the Earth's gravitational pull. If something comes in from infinity and falls into the Earth, it will have that speed when it actually hits. So nothing hitting the Earth would have a velocity less than about 11 kilometers per second. I hope that's fairly obvious. Here's just a nice little pretty picture showing the Earth going around the Sun. And as I'm sure many of you know, its speed is about 30 kilometers per second. So what speeds will we have if we're impacted by something? Well, as objects come in towards the sun, they convert their gravitational potential energy into kinetic energy. Just like if you had a car at the top of the hill, let the handbrake off and it runs down, it speeds up, it converts the gravitational potential energy you have into speed. Now, as it happens, it doesn't really matter where things come from. When they get to the distance of the Earth from the sun, they'll all have a velocity of around 30 kilometers per second. That's just a given. It is why it's so hard to send a spacecraft to Mars. To Mercury. Dead easy to get there, but you've got to stop because you're going faster and faster and faster. And to do that, they had to do lots of gravitational slingshots. Now, when you go out to the outer planets, you use them to speed you up. But here, they had to use these slingshots to slow them down, to finally get into orbit about Mercury. So we've got this 30 kilometers per second. So the impact velocity then is dependent on the direction of arrival. If it comes from behind the Earth, so it's moving up relatively slowly to us, the impact velocity will be quite slow. At a minimum, as I've said, of 11 kilometers per second. It will speed up as it just approaches the Earth. On the other hand, if it approaches from the front, the impact velocity could be up to 60 plus 11 kilometers per second. So we have a range of impact velocities of 11 to about 71 kilometers per second. So you'll see a couple of numbers coming up later on which are within that range, city hopefully. Well, an interesting one that we all perhaps have been aware of was the Chevelink meteor, if I can say that correctly, in 2013. Because in Russia, there's been a lot of these problems of cars braking in front of you to claim for whiplash injuries. Many drivers there have dash cams. And a lot of these actually capture the impact. I think it was around the time people were going to work. And from all these images and knowing where they were taken from, they could actually plot the trajectory of the impacting object really quite well. And there's another one there. And here, that doesn't look like a dash cam to me, but someone took this rather lovely picture of the cloud that was produced as it came in through the Earth's atmosphere. Now, a problem. There was a great flash. So people in their offices went to the windows to look out. Shortly afterwards, the shockwave came and blew those windows in, causing many, many facial wounds. That was a bit sad. So if you do see a big flash of light, perhaps don't go to window for a short while. Anyway, they discovered in the ice this hole, and in there they picked up what we believe is the largest part of that particular object. Rather lovely, isn't it? So that's the most recent large event that we know of. So a little bit there about impacts of asteroids. What about comets? Well, I would say they're some of the most beautiful objects in the heavens. Someone called them dirty snowballs. As a comet comes close to the sun's heat ablates the ice and releases the dirt as dust particles. And the comet then forms two tails. The dust tail, these are the heavier particles of dust. They're seen by the light reflected from the dust, and basically it spreads out along the orbit, which often can be curved. And depending upon the orbit, sometimes it appears to be in front of the nucleus or coma of the comet. We call it an antitail. It's simply the way we observe the orbit of the comet. Now, there's also ionized gas, and this is very light. And so the sun's radiation pressure can force it to go away in a direct line away from the sun. I think that was first discovered by Peter Appian a long time ago. And they tend to be bluish, it's cyanogen, and as I say, they tend to be straight as well. So you get these two tails. There we are, a gas tail which is straight, leading away from the sun, The nucleus is right at the heart, you can't see it there, and we have a coma, and the dust cloud, which lies along the orbit, and that's often curved. So here's the sort of idea. Here's a comet coming in towards the sun. About 5 AU begins to form a coma, and you can begin to pick it up. As it gets nearer, the tails form. Here, the dust tail is beginning to curve. Larger particles lie along the orbit here, and you get some pushed out by sunlight, the lighter parts of the dust, but you don't see that very easily. And then the plasma tail, or the iron tail, is lying away from the sun. Here you see. So finally, between about 3 and 5 AU, the heating diminishes, the two tails disappear. So there we have a nucleus at the heart and the coma around it. It's a gas driven off from the comet. It forms a spherical coma, as it's called, and it can be 300,000 miles across. And the tail can be up to 100 million miles long. And these are the largest objects that we can actually see in our solar system, the tails of comets. The comets are pretty big too, aren't they? Well, there are two types of comets. There are the comets that we see once and once only. They come in probably from what's called the Oort cloud, although, in fact, Lembic-Opix, you may have heard of him. He married, I think, was involved with one of the Cheeky Girls, and I actually was with him and one of the Cheeky Girls at a party, and I couldn't see why he was interested, but still, he was. Anyway, he reckoned that his grandfather, I'm sorry, had probably proposed the idea of the Oort cloud before Oort did, but Oort made it popular. So he thinks it should be called the Lembic Oort cloud. And he said, if I said that in the astronomy textbook, what I was writing at the time, he'd take me for lunch at the Houses of Parliament. Well, I did put it in my book. It is there. In fact, although that book was published in 2007, it's still earning me quite a bit of money. It's been quite a good thing. It's only a small little textbook on astronomy, but it's done quite well. Anyway, sadly, by the time that came out, he'd been ousted from the Commons, so I couldn't take up my lunch. Now, when these comets come in from a great distance, as I say, a lot of them just go around the sun, go out again, and never to be seen again. But if they come close to Jupiter, or less often Saturn, the gravitational field of those two planets perturbs the orbit, and they may become what are called short period comets. And these then come round on periods which are comparable to our human lifetime. And that actually shows you a plot of the orbits of many now of the short period comets. And you can see many of them have their most distant point from the sun around the distance of Jupiter. They've obviously all been captured by Jupiter, but there are rather fewer that go out to the orbit of Saturn. That is where they must have come quite close to Saturn, and Saturn's perturbed their orbits. Well, I'm sure you all know that the most famous comet of all is Halley's comet. He observed a comet in 1682, and he was able to compute the orbital elements, not only of the comet he'd seen, but of those that had been seen in 1531 and 1607, I think one by Peter Appian. And the orbital elements were essentially the same. So he deduced that it was one and the same comet. So here are his words. Many considerations incline me to believe that the comet of 1531, observed by Appianus, that's Peter Appian, to have been the same as that described by Kepler in 1607, which I again observed when it returned in 1682. Whence I would venture confidentially to predict its return, namely in the year 1758. Now, you've all heard of Charles Messier. He was a comet hunter par excellence, and he spent a lot of time during that year searching for this comet. But sadly for him slightly, it was first seen and hence discovered again on Christmas Day, 1758, so towards the end of the year, by Johann Georg Lisch. He was a German farmer, but a very keen amateur astronomer. So that was the predicted return in 1758. It's now called Comet 1P. That's the first periodic comet Halley. And we can look back through history. It's rather fun. I think the first records of it date back from May 240 BC. It appeared in the east and moved northwards, as seen in the Chinese records. And I hope some of you can read that and probably translate it, but I'm afraid I can't. Then on the 12th of November, 164 BC, it was noted on some Babylonian tablets. In 87 BC, again recorded by the Babylonians. They were very, very good astronomers. And you may have heard of the Antikythera mechanism. We believe that that was actually based on all the observations made by the Babylonians. And it is the most wonderful device. And how it could have been built before the birth of Christ, I have absolutely no idea. But look it up. It's a wonderful machine, an analog computer. And I cannot understand how they could possibly have done it when they did, but they did, all based upon the wonderful observations of the Babylonians. 12 BC, recorded in the Book of Harmony. And by the way, we don't think it was the Star of Bethlehem. It was not anywhere. I think Christ might have been born 5 BC, but certainly not 12 BC. 1684, it's in the Nuremberg Chronicles. Sorry, my words aren't coming out too well. 837 AD, a very close approach, 3.2 million miles. The tail stretched 60 degrees across the sky. Wouldn't that be wonderful to see? Then, of course, perhaps one of the most famous returns at the time of the Battle of Hastings, as shown in the Bayeux Tapestry. And I've just enlarged it here. Here it is. And there it is. Isn't that wonderful? I think that's the most classic image of a comet that exists. And you see it on quite a lot of stamps. And notice that one on the bottom right, it will be back again in 2061. And sadly, I'm not going to be around then, but I did see it on its last apparition. 1145 AD. Nice picture of it there. Showing multiple tails. Well, that can happen. Bifurcation. This I love. Giotto di Bondeni. That name you might have heard of Giotto. We will come to it shortly. He had observed Halley's comet in 1301. He thought it might have been the Star of Bethlehem. So when he produced this wonderful icon called the Adoration of the Magi, it's in the Arena Chapel in Padua, and I would actually love to go and see this. He actually produced it in the picture above the crypt. You can see it here. Many years ago, the Open University used to have programs on BBC Two in the early morning. Many of you won't remember that. They were black and white. But there was a wonderful series on art, and this was a painting they covered. And he, in fact, was the first artist who used shadows to try and give a feel of dimensionality. Lovely picture. And you'll see why Giotto comes up a little bit later on. In 1910, it was visible. Having said that, there was a great comet of 1910, and many people who thought they had seen Halley's comet have probably seen the rather brighter Great Comet of 1910. And there are a few pictures of it. And Nick digitized an image just showing you some colors there, which are probably not real, but gives you an idea. That was 1910. And there were some lovely postcards there. And you can see them. Look at the trams they had wherever this was. Fifth Avenue and Broadway, that's obviously in America. This one, I wouldn't like to say where that was, I can't read it, but doesn't it look lovely? And they sort of showed this wonderful tail. To be honest, it was not as bright as that, but nevertheless, that was 1910. This is the orbit, and you can see it came close to the sun and the earth around then, but also it was furthest away in 1948. So since 1948, it was coming in towards the sun, and now of course it's going out again. It'll be furthest away from the sun in 2024. This was the recovery image. And I'm quite impressed. 1982, when it actually came past in 1985/86. So there it is, a little dot, just as the coma was beginning to form. It wasn't that spectacular. That's one picture of it that I found. That's another one there, showing the dust tail and the iron tail. Now, British United Airways, based in Manchester, thought it'd be a great wheeze to take people up in their, I forget what the aircraft were, it doesn't really matter, but they had therefore Halley's Comet flight every evening for about getting on for a month. Well, they took the first group up, and to be frank, the comet wasn't very bright, even if you're above the clouds, and no one saw it, which got them very worried. So that next morning, they rang up every observatory in sight in the north of England and said, could our astronomers go out and fly on these aircraft to show people where to look? I went out, I think, on 3 flights, and on each of those I was sitting in the cuddy seat, which is just behind, in the middle, behind the 2 pilots. What was very interesting, actually, was you could actually hear what the pilots were saying to each other, but not being sent out into the cockpit. And as we were sort of landing on one of these flights, there are 2 throttle levers, one for each jet, and they should be basically side by side, so you move them together. But they were way out on this particular flight, and the captain said, there's no way this plane should have actually been allowed to fly with the 2 controls so well separated as they were. That was interesting. The other interesting point about this, on one of those, I think it was towards the end, and Halley's Comet was pretty low down, I actually do have an excuse for lying on the cockpit floor with one of the air hostesses, because that was the only way I could show her where it was. And in fact, one of my colleagues, Ralph Spencer, also had the same pleasant experience. But I was a lot younger then, as you can imagine. Now, I mentioned Giotto de Bondone. Well, ESA produced a spacecraft to go and visit Halley's Comet and image it. It was live on television. Here's the picture of the spacecraft. This was pointed back towards the Earth, so we had live pictures, and this looking, a heat shield here, little camera looking around the side to actually photograph. I said a heat shield, I'm sorry, an impact shield. It was trying to protect everything from all the dust particles that you'd find close to the comet. My apologies. Well, I watched that live program, and it was a disaster. None of the people, which included Sir Francis Graham Smith, our boss at the time, had any idea what was going on. The only sensible comments were made by a 16-year-old boy. And quite what he was doing there, I don't know, but he did say some sensible things. It is said that Maggie Thatcher said, if this is how we waste all our money on astronomy, I'm cutting the funding. And to some extent, that did happen for a while. However, when they actually did process the images, they were quite good. So here you see all the outflows coming from the comet. Obviously, the sun is on this side. More about those outflows a little bit later on. So that was the first image, close-up image of a comet done by Giotto. Well, obviously, the best comet we've had in perhaps many of our lifetimes was Comet Hale-Bopp. Lovely picture here showing the dust tail and the wonderful iron tail. A few more pictures of it there. I took a picture of it. We were using our Lovell telescope to study the gas in the tail. So hopefully that it should be looking towards the comet. And I was out there that evening and I took that photograph. Notice Jodrell Banks' early warning sort of rocket system to protect us that we have on the grounds in our visitor centre then. Anyway, that picture was shown in, I think, Astronomy Now or Sky at Night magazine. I think Astronomy Now. It was only about 2 inches across. And there was this terrible letter saying, look how bad Jodrell Bank is. It's totally light polluting the whole of Cheshire. See how bright it is. Well, I wrote back, and it was published in the next issue. If our telescope being lit up was destroying the view of the heavens from Cheshire, how could I possibly have imaged the tail of the comet? This was, of course, a long exposure photograph, and that's why the telescope looks very bright. And in fact, to be honest, you can barely see it. The lights we have them on them as low as possible. And some time back, in fact, the chief engineer and I did a walk around, and we made a study of all the lighting on the site. And now it is all things that look down. We try and minimize the light that we have from the site. And in fact, there's a sand quarry quite close. It produces vastly more light than we do at Jodrell. So we do our best. Last year we had a comet, did we not? Comet Neowise, and I did take 3 pictures of it. Not sure this one can't come out perfectly. In fact, the last time any of us astronomers, or we astronomers, were able to go out as a group, about 6 or 7 of us, went up into the hills above Macclesfield, and I took this picture of the comet. I call it Comet Amongst the Stars. I'm sorry that it's showing a little bit of color around the edges. I sort of just got the bifurcation here. A little bit of bifurcation was visible on that night. Then it got cloudy, but then another day, a little bit later on, I took this picture looking over Manchester, and you can just see that was actually quite a transparent night, wasn't it? This actually is a vertical panorama. I think I had 3 horizontal images stacked together or put together. And then after having taken this, I went around to a rather lovely location called Reedsmere. And if anyone, I think, can remember the talk I gave on astrophotography some years ago, I did a nice star trails image taken from this very same spot. And here we see the plough. There's Polaris. Here is Cassiopeia over here. And this is due north. And there's the comet. But again, it wasn't very large and not really very, very bright. So since then, or since the time of Giotto, other spacecraft have visited comet nuclei, as I'm sure you know. This is a picture of Tempel 1. This is 103P Hartley. And I just want to mention the point here. Look at all these outflows. This means that comets are jet propelled. It was a long time before I realized this. That means that if you know the orbit before it comes towards the sun, you cannot immediately deduce the orbit or calculate the orbit of it when it goes past the sun or comes away from the sun. Because during that time, it will actually have been firing its jets and adjusting its orbit. So orbits will always change as one of these comets goes around the sun. This, of course, is perhaps the most famous one, 67P Churyumov Gerazimenko. And this was the one that was visited by the Rosetta spacecraft, which launched a little lander called Philae. And I don't know if that's an artist's impression or whether that was taken from Rosetta as it left. But anyway, that's it leaving the mothership. The objective was to go down, land on the surface, lock onto the surface. These things here were meant to shoot in to the surface and lock it on to capture it. Sadly, that didn't quite work. And so it actually bounced across the surface. And they didn't know what happened to it until more recently. They were able to spot this little thing here. Quite why that looks like Philae, I don't know. But there it is, trapped underneath an overhang. What a pity that was. Well, this is a wonderful comet. And somebody may remember this, Shoemaker-Levy. It's a comet that impacts, or the parts of it impacted with Jupiter. Eugene and Caroline Shoemaker, a wonderful couple. Now, Eugene Shoemaker, he was a geologist, an expert on impact craters, and craters in Australia, on the moon, and on Eros, are named after him. He wanted to be an astronaut, but I think physically wasn't able to do so. So instead, he taught the astronauts about lunar geology. And later he realized there was a threat to mankind from asteroid impacts, and with his wife Caroline, set out to detect them. David Levy, on the other hand, was a discoverer of several comets, as we will see, and he joined them in this quest. Together they discovered several more comets. He discovered Comet Levy, or Levy, I should say, in May 1990, and that's his telescope. I once met him, a great guy. Now, I might say, I also discovered that comet myself. This is M15, a wonderful globular cluster in Pegasus. And I'd taken my family to the southern part of France. We were staying in a campsite, and on a lovely clear night, I was showing some of the people on the tents in our little sort of area of tents what you could find in the heavens, southern Brittany to be precise. And the last thing we looked at, I said, well, let's try and see if we can find a globular cluster. And we looked at M15. And I said, my goodness, that's far brighter and more visible than I've ever seen it in Manchester. Now, I knew, of course, A, it was higher up in the sky because I was down in France, but also, of course, there was virtually no light pollution. I was quite impressed, and so were all the people who looked at it. But a couple of weeks later, when I got home, I came across this picture, or these pictures. Here is the globular cluster M15, and here is Comet Levy. So I serendipitously, I can't say that, discovered it totally by accident about a month later. So it doesn't count at all, does it? But that was rather fun. But I was really, really confused about what I was seeing. Now, in 1993, they took an image with a 0.46 meter telescope that showed what appeared to be an elongated comet. They then got the Hubble Space Telescope to image it, and this is what the Hubble Space Telescope found. Not one long elongated comet, but a whole series of nuclei, coma, and tails. About 26 major objects in that group. So, of course, with observations over the next few months, they could compute the orbit. And it was realized that the following year, those individual elements would impact on the surface of Jupiter. And there's the sort of idea. So this train of small cometary particles would come in and impact on the surface. And these are artist impressions. Now, these aren't very accurate, in fact, because these impacts are about one a day, and that looks as though they're all going to happen, in a very short time. But nevertheless, artist impression. But the thing to notice here, they were going to impact a bit round the back. Only one spacecraft, I think, was able to image an impact, and that was, I think, Galileo on its way to Jupiter. So it was way out to the left. But from the Earth, no one could actually see the direct impact site. Oh, these are lovely artist impressions, aren't they beautiful? Hubble did, however, observe the fireball of the G impact site. The G impact site, G object was probably the largest of them, and there are some images showing the actual fireball rising up above the surface and then falling down and flattening. So that was the only really direct observations we had from Earth. And then we had these wonderful images coming back showing these scars on the surface. And this is the one that I feel most interested, or I like the most. Now, obviously, we all wanted to see if we could see anything. I never thought we'd see anything on the surface of Jupiter. But we had a couple of fairly cloudy nights. The first clear night after these happened, I went out with a few of my colleagues to the car park at Jodrell Bank, where we have a very good low southwestern horizon, because in fact Jupiter was only going to be visible as dusk fell, and it would be very low down. I had with me a 10-inch Newtonian, a Dobsonian, and I looked at it and I saw these two spots on the surface, just like that actually. And I could barely believe my eyes. I rushed across to one of my colleagues and had a look through his telescope, and I couldn't see them. But then I saw them down at the bottom, not at the top. And of course, he was using a cat, I had a Newtonian, and things were upside down. Now that was quite pleasing, because the fact that I hadn't seen them where I was expecting to see them, but then saw them where I wasn't expecting to see them, meant that I probably had seen them, if that makes any sense. And in fact, we all managed to see it. Now, it could have been we were some of the very first people to actually see these spots in Europe, because most of Europe was in fact in cloud cover, as was most of the UK south of us. Patrick Moore was actually at Hurst-on-Sea with a group, maybe some television people there hoping to see it. And I had to ring him up from Jodrell Bank and say, any luck Patrick, he said, no, I'm sorry. And I said, well, we had seen it. So that was quite exciting. There are some things you see through a telescope that you'll never actually forget. And that's one of them in my fairly long lifetime now of observing an image in the heavens. A very nice ending point to this story. Sadly, Eugene Schumacher, who went every summer to search for impact craters in Australia, got killed in a car accident. And some of his ashes were placed on this little spacecraft that was going to impact the moon. I might say you're not allowed to impact things out in space. So what you have to do is you put this object in front of where the moon's going to be and let the moon impact it. I hope you realize there's a subtle difference there, and that got around some of the legal problems. So finally, near-Earth objects. These are the things that could be a problem. They're objects orbiting the sun, whose orbit brings them to within about 1.3 astronomical units of the sun. Many of their orbits, as we shall see, will cross that of the Earth. The vast majority are asteroids. We call them NEAs, near-Earth asteroids, but few are short-period comets. And there are now, the latest number I could find, about 25,000 near-Earth asteroids are known, ranging from 50 meters to about 32 kilometers, which is the largest, Ganymede. The second largest is Eros, which in fact was the target for a rendezvous mission called NEAR in 2000. And I don't know how clear that is, but can you see all the orbits of these near-Earth asteroids? You can see the Earth, and you can see that many of them will actually cross the orbit of the Earth. Now, 2,100-ish of these near-Earth objects are classified as potentially hazardous. And those whose orbits approach the Earth's own path around the Sun to within 4.6 million miles, whilst also measuring greater than about 110 meters in diameter. Because when you get to that size, you could have some local significant events. The ones that we're interested in, they're called the Apollos, the A10s, and the Amors. Now, we don't have to worry about the Amors too much. Currently, their orbits do not cross that of the Earth, so they couldn't impact. But it may be they can become perturbed and in the future could do. There are then two types which are Earth orbit crossing. The Apollos, which you see there in green, are largely spend their time outside the Earth's orbit, but they too come in, they get closer to the sun and then go out again. So they cross the Earth's orbit twice. And then we have the A10s, which spend most of their time actually within the Earth's orbit, but they cross it once on the way out beyond the Earth's orbit and once back on the way in. I think perhaps you can see them there. So it's the Apollos and the A10s that we have to think about at the present time. But occasionally there's comets. This is Comet Linear, and that one came fairly close sometime in 2000. The number of near-Earth asteroids over 1 kilometer, and those are the ones you really worry about, is between about 500 and 1,000. They only survive in their orbits for a few million years until they either collide with the inner planet, which of course includes the Earth, they're ejected from the solar system by close approaches with planets, or they fall into the sun. So quite a lot of them will eventually hit the inner planets. A slightly complicated plot here, and there's another version of it to come, not as pretty. But basically, this line here shows you the diameter of the comets and the amount of the asteroids, the amount of energy they'll release when they hit the Earth, which is along here, and over here, how often they're likely to happen. And the important thing, of course, is that those that could be a real problem, like the impact of the Chicxulub impactor here, somewhere down there, is probably going to be happening on tens of millions of years. Things like Tunguska, which are still could be quite bad if they hit either anywhere near a populated center, or if they actually impact in the sea, they cause tsunami, which could be a real problem. And that happens, well, that's 10 squared, 100 years. So it's between 10 and 100 years, something like that will happen. And this one up here, I think we'll see on this one here, is the Chevelinx one, the Russian one. So these are ones that have been discovered recently in green, and that's where they've been seen. But infrasound means they've been detected by sound as well. This is the Russian one here. There's Tunguska, and of course down here is Chicxulub. Happily, these things don't happen very often. Otherwise, I probably wouldn't be talking to you. So how can we search for NEAs? Well, that Shoemaker-Levy 9 impact series was a wake-up call. And even governments realized that things could hit the Earth and maybe be very destructive. So Project Space Guard was set up. And the idea was to detect, as we shall see, all of those asteroids that could be a major problem for the Earth. So in 1998, NASA was tasked by Congress to catalogue at least 90% of all the large NEOs. And those are those of 1 kilometer or more in size. And they had about 10 years they were told to do it in. And these would be large enough should they strike to Earth. To strike Earth, it would result in a global catastrophe. So quite a number of telescopes are built. Now, I believe in October, are you not having a talk about the LSST? I think you are. I spotted that earlier on. The Large Synoptic Survey Telescope. These are wonderful things. And they're basically designed to have very, very wide fields of view. They tend to have multiple mirrors and corrective lenses to give you these wide, flat fields that you can actually detect many, many objects at one time. I mean, they're surveying the sky the whole time. This is Pan-STARRS. You can see what it says there. That again has a 1.4 billion pixel camera. Well, I've got a 24 megapixel camera, so you see there's quite a difference there. And that is because the telescope produces a wonderful broad flat field. It can image so many stars at one time, and or of course asteroids. And each little OTA, they're called, is an 8-by array of 600 by 600 pixels. That's probably the largest CCD camera in the world, I suspect. And just a matter of interest, it's imaged M51, the Whirlpool Galaxy. It's not actually pretty close to the image I took the other night using an 8-inch modified Newtonian. But it shows you what it can do. And that's a picture taken, a big mosaic. It's not quite complete, so you can see, of the Andromeda Galaxy. But it is a pretty amazing telescope. And we can say the success. Here, it's pretty, isn't it? These are the known NEOs of Jan 2018. I couldn't find one more recently. But there you see the Earth, and you see all these wonderful things going around. And basically, NASA, as I said, worked with a number of ground-based observatories as part of the Space Guard survey. And they've reached that goal. By now, they've now catalogued an estimated 95% of all NEOs over 1 kilometer in size. None of these pose any threat of impact to the Earth any time in the foreseeable future. Not so that smaller ones can't, but none of these really large ones, which would be globally a real disaster, look as though are any problem. This is an interesting one. This is asteroid Apophis. And from its orbital elements measured some time ago, it was thought there were possible impacts in 2029, 2036, or 2068. Now, by the way, you might have noticed some years ago, there were lots of newspaper headlines saying, asteroid blah, 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 could hit the Earth next week, or something like that. Quite dramatic headlines. Now, what happens is this. When an asteroid is first detected, an NEO, the orbital elements aren't known very well. And so the error bars on its orbit are quite wide, and they can then encompass that of where the Earth will be. However, in the next few days and weeks, the orbital parameters are made far more accurate, and then 99.999% of the time, it will not then impact the Earth or come that close necessarily. And so they've now barred all results, initial results of asteroid detections from being published. until they're sure of the orbit. This is one where they didn't quite know until March this year, actually, and those are bistatic radar images, March the 8th, 9th, and 10th. It didn't look very good, but from that, they could get superbly good orbital elements. And in fact, we now know that this particular asteroid will not impact the Earth on any of those 3 dates, which is comforting. And that's a pretty picture. It's going to fly by 28, just outside the orbiting geostationary satellites. So it's going to be pretty close, but not too close. So finally, how could we avert disaster? Well, not as it was done in Armageddon, which you may remember. Bruce Willis led this team, and they basically blew up a nuclear bomb in the asteroid. The problem is that this would make lots and lots of individual bits, and they would all hit the Earth, and the effects would be pretty much the same. You cannot blow up an asteroid or even deflect it when it's close to the Earth. It's moving too quickly, and anything you do will just produce a train of smaller bits that will then hit the Earth. I will say about that film, the music as they land at the end, I think is quite fantastic, but many of you will not perhaps know what that is, but it's rather good. So what you have to do, now look, I think you saw one of those earlier pictures. When a comet or an asteroid for that matter is furthest from the sun, it's moving quite slowly. As it gets nearer and nearer to the sun, it goes more quickly. When it gets to about the distance of the Earth, it's going at about 30 kilometers per second. The only way you can prevent an asteroid hitting the Earth is if you get to it when it's furthest away from the sun. There it's moving very slowly. And again, that analogy of a car on the top of a hill which starts running away. If you could get to it very quickly, you might be able to put on the handbrake and stop it. But once it's got going, you've had it. So we've got to know where these things that are going to hit the Earth are accurately enough so we can get to them when they're furthest from the sun, and then perhaps we can do something. And they're talking about either a nuclear bomb or a gravity tractor, I think, just to put it away. And to be honest, you don't have to change things an awful lot. If you can just slightly change the orbit when it's as furthest distance from the sun, you can quite easily make it miss the Earth, which you see over here with the moon. And a solar sail, that's another thing you might be able to do. I like this one, they're called mirror bees. And the idea is to reflect light from the sun onto the surface. Obviously, if you get enough temperature, the surface will ablate, particles will come off, it will act like a little jet engine, and that will alter its orbit. And I don't quite know on that picture why they've got the Earth there. This would have to be done where the Earth is nowhere near at all. So there are ways, and people are thinking about that quite seriously. And I would just say this. When people say, is it worth doing astronomy? Have astronomers ever done anything for us, like the Romans? One answer is yes. They will, quite soon, have been able to plot the orbits of all the asteroids that could be a problem, and hopefully find out in sufficient time so that something can be done about it. We could, in fact, save the human race. And I think that's a good thought. So when anyone says, why on earth do you do astronomy? That's one thing you can say. Now, this was something I thought about, 10 or 12 years ago when I was actually giving lectures at Gresham. We cannot say that we will not get an impact. I think we're pretty safe from asteroids because we can see them. We know what's going on. There is, however, a problem with comets. Often, you first detect a comet when it's relatively close to the Earth. There's nothing you could then do. And it's even possible, so I am told, that a comet can sneak up on the Earth in daytime, so you'd never even know it was coming. That might be a good thing. But I did wonder whether we should take out some insurance to preserve our human race in the event of a major impact. Now, of course, when they were worried about nuclear war, they had all these bunkers where they kept all the important people. I don't think you should do that. However, some of you may have been to Center Parcs, which seems very expensive, but I think you know that they have this big dome. You can just see it here. inside of which is a sort of a bit of a paradise. So it doesn't really matter what the weather's like, you can enjoy yourself. You may remember the film with Jim Carrey in it, where he basically is trapped in this pseudo world being filmed all the time, and he tries to escape. There you see him trying to escape. I wonder whether deep underground, 2 locations, not opposite the Earth, because if you impact one side, then the shock waves will travel around the Earth and they'll actually have a major effect on the opposite side of the Earth. So they don't want to be opposite each other. But well apart, deep underground, things like that, where perhaps for a fortnight, a nice ethnic group of people would go and actually stay for a couple of weeks, something like going to Centre Parks. But down there'll be sufficient materials, oxygen and whatever to keep perhaps you alive for maybe a few months. So if we did get a major impact, at least a group would survive, and perhaps they could keep things like seeds and that sort of thing. I know we have these places on the Earth where they do keep seeds and seed banks and things like that, but that's just a thought. Actually, I managed to do it quite well in an hour. It's a new talk, so I thought we might be going to midnight. Finally, a simple rule for life. You never know. Enjoy every day to the full. There we are. But let me just say one thing. I do spend quite a bit of time. I've now written about 200,000 words or more in over 100 articles on my Astronomy Digest. That's the website. Morison's only got 1 R in it. It's an unusual name, but if you've actually been doing some writing, you might find it's in Times New Roman font, and that was actually produced by one of my great uncles. Anyway, with a single R. If you just search for Astronomy Digest on the web, it will come up. I feel a bit bad about saying it's Professor Morison's, but at the time, Brian Cox was being very keen about being Professor Brian Cox, so I thought I'd try and do my best to equal him. Anyway, there are lots of articles there about instruments, lots about refractors, Newtonians, Maksutovs, anything you like. There are articles about, but an awful lot of articles about astrophotography, starting from square one and how to go about it. So some of you might find that interesting. It has about 4,000 views a month, so it can't be too bad, I hope. So there we go. I'll stop screen sharing. And there may be some questions in the chat. I don't know, but over to you, sir.
Well, thank you very much, Ian. That was a marvelous talk. So yes, do put some questions in the chat. I can see at least one in there that we'll perhaps come to. I
noticed there seem to be only 4 people, but that's just us.
That's just us, yes.
On YouTube. I hope
a lot more on YouTube. Yes.
I hope there are a few more on YouTube. That's all I can say.
Yes, there is quite a number there. I was just wondering, do you know if we've ever been hit by a comet, or all the impacts we've?
Well, the Chicxulub one, they don't know if it was a comet or an asteroid. They actually do not know. So I can't actually say yay or nay. I think the Tunguska, they're pretty certain, was a stony meteorite, and obviously the one in Shevlink's one was also one because they've got bits of it. So the answer is I don't know, but I don't think it's been proven. But I've been looking at the Chicxulub websites and things in the last few days, and they still don't seem to know which it was.
It is.
And I mean, comets are far more amorphous things and not so dense as asteroids. But if they're big enough, I guess they can have much the same effect.
I imagine so, yes. You wouldn't want to be hit by a many tons block of ice, would you?
You would not. No. Well, by that time, the ice would have ablated. It would have evaporated, wouldn't it? But they may well probably more like to cause airbursts than impact,
yes,
I suspect.
I imagine so, yeah.
But that's a thought.
Let's see, there's one in the question there from James. Says, if the object comes from behind at 11 kilometers a second and the Earth is traveling away at 30 kilometers a second, it can't catch up.
No. He's mixed that up. I'm sorry, my fault. Right. It's got to be coming towards us at around 30 kilometers a second. Otherwise, it can't catch up. You're quite right there. But then, because of the Earth's gravitational speed, as it gets close, it will speed up. So it will actually hit the Earth. Well, there's a zero relative velocity because of its motion. but you've got the 11 kilometers per second due to the fact that the Earth is going to pull it in. So that's the minimum impact velocity. Does that make sense? It's got to be going at 30 kilometers a second, otherwise it couldn't catch up at all. That's the first thing, obviously. But then it will, in fact, and that means as a net result, pretty much, it's got to be going slightly faster than 30, obviously. But then you've got this additional 11 kilometers per second. Does that make sense? I hope so.
Yes. Yeah.
I may not have been clear enough when I said it before. Hope that's okay. Was it James?
Yes. I'm sure it was. Yes. Yes. You did say, yes, we've got a talk from Steve Barrett on the LSST coming up. So yes, that should catch quite a lot of comets, I imagine, and asteroids.
No, I think that will be fun. In fact, in a way, I might email and say, "Can you let me come and listen to it or watch it?" Incidentally, there is a talk. I love the way you put your talks up on YouTube, and someone has put one up on the is the iStellar.
Unistellar.
Unistellar.
Yes.
Which I want to watch. I only found it today, and I haven't had time to look at it, but I will do.
Yes.
I gave a talk to my own society about plate solving, and this is one of, well, two telescopes. The other one is the Veonis. There's another company that makes them, makes two, and they basically are semi-automatic, and they plate solve to find out where they're looking and do everything automatically, which is quite wonderful. So I want to watch that, and I hope he's had good fun with it.
Yeah. I'll send you the link, Ian, after the talk so you can have a look. We did it last month.
Yes, thank you. It may be I can pick it up off your website, but if not, please send me the link. I'd love to watch it.
Yeah, it's on the website as well.
Yeah. Thank you. Anybody else?
One,
Shirley says, thank you very much.
one just above that. How realistic is deflection of a comet with a nuclear blast? How far away would the rocket taking the nuke have to take it to have a realistic chance of deflection?
A very long way away.
Right.
And that's the trouble. I don't think you know about comets soon enough to get to them. The great thing about asteroids is they have these orbits. They go in past us, we discover them, they then go out again for maybe 50 years, and hopefully we've got time to do something about it. No, I mean, I do think comets are the problem. I really do. Although I do think it's very likely that it's far less likely we'll be hit by a comet than we will by an asteroid. Hopefully we won't be hit by an asteroid because we'll know what to do about it.
There is I believe there is an ESA mission now approved to try and divert.
Yes, there is. The first try, and I forget what the name is. I
can't remember either. I know Alan Fitzsimmons is involved in it.
Yes, no, that's going to be very good. As long as they divert it so it actually hits the Earth, it's all right.
Yes, take a perfectly safe one and divert it to hit.
Yes, that wouldn't be good, would it?
Less than perfect.
But I think that's going to be possible. I really do. I think that we will be able to sort it out. And Shirley said again on the nuclear blast, would that affect the Earth too? No, it's got to be too far away. If you're going to do it, it's got to be so far away it will not hurt the Earth. And of course, you can't get a shock wave transmitted through space, so that's a help as well. There will be the light. I mean, if you were looking up, you'd see it, but I don't think we'd be in problems. Oh, what camera do I use for my photos? That's a very good question. Thank you for that. Right. Well, a lot of the articles on that website have been taken with DSLRs and mirrorless cameras, because I'm sort of trying to write a book about them, and I've been using those pretty solidly for a couple of years, both wide angle images, which basically the ones I took of the comet over Manchester and over the Reedsmere, but also with a telephoto lens of the one which showed the two tails just about. I also use them on my telescope, larger telescopes. There's a very lovely little mount now called the Explore Scientific EOS something 100, which costs about 400 quid, a bit less, which is actually doesn't have a hand controller. I control it from a little laptop, and it's belt driven, and it tracks extremely well, and it makes a very, very good star tracker, seriously good star tracker. But also it can actually cope with up to my 90mm. I've got a very nice 90mm refractor. It will handle that quite well too. So that's a lovely portable thing. Quite often our society goes up to a place called Teg's Nose, to the southeast of Macclesfield, where it's fairly dark. And that's someone, I hope to take it there before too long, says he, hopefully. And also I've got a much bigger mount as well with bigger cameras. Just recently, I've actually bought myself, well, I have had for a long time 2 CCD cameras, one mono and one color. But I've now got a Altair Astro Micro Four Thirds cool camera. ZWO sell almost identical ones actually. Normally they're about £800-900, although I got mine. Everything I buy pretty much is off UK Astro buy sell. I daren't look at it because I find things I want to buy, but usually I buy things at about 2/3 to a half of their new price, and generally speaking, you get very, very good value for money that way. Anyway, I've got one of those now, and I've been using that to take pictures of some of the galaxies. Yes, like M8 or M56, some of the well-known galaxies, M101 and the likes, but also just the last week or so, some of the globular clusters. So I'm having fun, but you can do an awful lot with a simple, particularly a mirrorless camera, because with adapters, you can actually use lenses from almost any old camera system. And you can buy some of these lenses, you know, for 50 quid or less. And they work very, very well indeed. And the one I've got two actually, I bought a spare. It's a Sony A5000, which is a 20 megapixel sensor, but it's APS-C, so it's quite a big sensor, and it does wonderfully well. You used to be able to get an excellent one for about 130 quid. I've been recommending it to lots of people. I know at least 4 or 5 of the people in our club have got them, and now you can only get a good one for about 140. So I think I've caused a bit of a run on that particular type of camera.
Not the price.
But you don't have to spend a vast amount of money. You don't necessarily have to have a tracking mount. If you take short exposures, and there's a rule, perhaps divide your focal length into 300, and that gives you sort of a maximum exposure time, even for a modern camera. And you can then stack them in a free program called Deep Sky Stacker. And anyway, there are lots and lots of articles about that on that website, so perhaps have a look. I think I've said enough on that, but thank you for asking. What else is there, perhaps? Do you know who first used the term? I have no idea. Harbinger of Doom. I just thought it sounds rather nice.
Yes.
I really don't know where that came from. I first gave a talk with that title, many, many years ago, although I think I lost it, and I've had to reproduce it from square one again, so not to worry. Tektite fields with fresh-looking tektites, but no obvious impact. I can't read the last bit. Hold tight, if I can move it. I can't. No, people's faces are in front of it.
Oh, it says,
I've got rid of people. Why is there where the impacts on? Sorry, there are lots of tektite fields on with fresh-looking tektites, but no obvious impact sites. Why is this where the impacts on the moon? Now, where are these fields? I wonder. I'm not quite sure.
No, I don't know if it's related to his previous question. Have they found the source of Libyan glacier?
Oh, right.
Might be.
I don't know. I don't think it would be on the moon. It must be an impact on the Earth. Remember those Moldovan tektite things, whatever they're called? They were caused by the rice impacts. No, I'm quite sure that they would be, in fact, the result of an impact on the Earth, which for some reason we don't actually know where it is. That's all I can say, I think.
John Hurst asks, do any comets have a contra-rotating orbit?
Oh, wow. What a good question. Do you know, I don't know.
I guess there must be some.
Well, I think there must be some.
Yeah.
But, I mean, most things go around the sun in the same way, don't they?
But we have had visitors from other...
yes, we have, and they've come in.
Yeah,
Look, the answer is almost certainly there are, but I have to say I don't actually know of one. That's my fault. My apologies. Good question.
Have you been to the Space Guard site near Knighton on the Welsh board?
I've been there a couple of times, and I know the guy that has run it. I was actually there with Lembic Erpic. Do you remember I mentioned him earlier?
Yes.
Because there was some special opening, and I was invited to go to that, and he was there. I don't think the cheeky girl was there with him. They were together, at a wonderful party at Patrick Moore's house in Chelsea, which was celebrating whether it's 50 years of Sky at Night program. Anyone who'd actually been on Sky at Night, and I have been a couple of times, his program, were invited, and that was a wonderful night. In fact, the best bit about it, I had a nice chat with Mylene Klass, if you know her. And that was by far the best. And she looked far nicer than this cheeky girl did. Anyway, that's another matter. I must be showing my age.
Have you considered the question of comets collecting and shedding life forms and thus distributing life?
Oh, panspermia.
Panspermia, yes.
Well, yeah, good question, isn't it? I don't know. I mean,
the jury's out.
Yes, the jury, I think, is out on that. This basically said, has life arrived on Earth from elsewhere? I find it hard to think it could come from anywhere elsewhere than in our own solar system. But it could be we're all Martians. You've probably heard that. Because Mars is smaller than the Earth, it would have cooled down more quickly. And we do know that about 4,000 million years ago, it had a lot of water on the surface. So the conditions where life might have formed occurred much earlier on Mars than it did on the Earth, because it took long to cool down. If life had once formed on Mars and an impact strikes it, material is thrown out into space. Apparently 6% of that material will actually fall on the Earth in the course of time. It's not impossible that if that happened, by the time we had some nice little lakes or ponds with interesting things in them, building blocks of life, then maybe life could have come from Mars. So that, I suppose, is panspermia, but I don't really think it's happened on any other in any other possible way. But there are various people that think that may be possible. So who's for me to say?
Right. Well, I think we've got to the end of our questions there. So,
oh, good.
Thank you very much, Ian, for a wonderful talk yet again.
Well, it's been very
good value.
It's been a great pleasure to be with you, and I hope the 4 people who watched it must have enjoyed it.
Well,
I don't know how, but I hope you have a few more than that. And I thought I put my mask on just to make sure you're all safe, but I have been double vaccinated for quite some time now, so probably all right. I hope everyone with you is okay. We've had no problems with any of our society members that I know of, so things aren't too bad.
We're all fairly safe as far as I know.
Yes, and Cheshire isn't too bad part of the country. However, the first talk I'm supposed to be going to give live is in Bolton.
Oh,
so I'm hoping that's going to be some time. I put that off until October. They did suggest it might be next month, but I said no.
Yes.
Anyway, not to worry. So anyway, it's been a pleasure being with you. All the very best for your society. And if you could give me that link to that particular video, I'd love to watch it, because I think it's really very, very interesting.
Right. Well, thank you once again. And perhaps see you next year in person. Who knows?
You never know. All the very best. Bye-bye, everybody.
Bye.
I think
Cheers, Ian.
Yes.
Right. So that concludes it for tonight. Just to reiterate, I think we've got the Milky Way coming up. Oh, there we go. Ah, wonderful. Richard. Fantastic as ever. So yes, the Milky Way on 17th of June. That's the sort of more informal one done by members. The JUICE mission, 1st of July. Dr. Chris Arridge from Lancaster, is it? University of Lancaster, I think. We're probably going to have a July meeting, the sort of more informal. We are wondering about doing it at the observatory. It depends a little on the weather and how well prepared we are and all those things. But that'd be really nice to see everybody again and actually meet people. If we do it there, we might also live stream it, depending on how good we are with tech, so that if you don't wish to come to the observatory or don't feel ready, then that's a possibility. But anyway, more on that as we get closer to that. We'll see how all that works out in due course. The barbecue will most certainly go ahead, 7th of August. Put that in your diary. I think it's going to be 5 o'clock in the afternoon. So fun frolics and whatever else we can scare up, come and have a look at what's been happening in the observatory by then. And should be a good evening out. Eat, drink, and be merry, all that sort of thing. And then we're into September and are more regular. We don't know quite yet when we'll be meeting in person for those meetings, but it could be September. We will just keep an eye on the situation and see where we can be hosted, and B, whether the country is open for indoor meetings at that point. So I think that's everything. What about anything I missed out, Richard?
No, I can't think of anything. Don't forget the partial eclipse.
Oh, yes.
Thursday, isn't it? That'd be
next Thursday.
Interesting to see if we get good weather.
You know what time it starts?
I don't know. I think maximum here is about 10:40.
Oh, in the morning.
I think, yeah.
And it's not a huge total eclipse, so you won't notice it unless you go looking for it. And do be careful if you go looking for it. Do use proper protection, as they say. Right. So I think that's everything. See you all next time, and stay safe, and until we meet again.